Welcome to your lecture for Chapter 21, which is all about nuclear chemistry. So we've been through electrochemistry and thermochemistry and thermodynamics and all kinds of other things. Well, here we are at nuclear chemistry. So this is all about radioactivity is the main topic for this unit, or for this chapter that is, okay? And there are three main types of radioactivity. Radiation, especially. Okay, the first of which is probably the most common and actually has been used in a number of very famous chemical experiments, i.e. the gold foil experiment. And this type of radiation is from alpha particles, or alpha emission. So it'll have the symbol for alpha. So alpha particles are essentially just a nuclei of helium-4. Okay, a helium nucleus. So with the symbolism, it'll have a 4, 2, He, and it's 2+. Okay, so it's just the nucleus, not its electrons. Okay, so we get 2 protons, 2 neutrons. Remembering from way back in the day, this is the mass number. So that's protons plus neutrons. This one is your protons, your atomic number. Okay, so way back, beginning of Gen Chem 1, we learned all this stuff. Well, now it's going to come back to haunt you. If you weren't confident on how to tell what the mass number was and what it meant, this is going to be a little challenging. So a nucleus of helium-4 is ejected spontaneously from certain elements. Certain elements. Okay, things like plutonium, uranium, things of that nature. Okay, so alpha particles, in comparison to other radioactive particles, are big. Okay, they're big particles, great big things with 2 protons and 2 neutrons, but their penetrating power is low. Okay, you can actually stop alpha particles with as little as a sheet of paper. But if you don't stop alpha particles, they will punch a rather large hole in your atomic structure, or the atomic structure of whatever you're shooting alpha particles at. So in the famous gold foil experiment, they were shooting alpha particles at a sheet of gold foil and quite literally punching holes in that material using these large, rather slow-moving particles. They are positively charged, right? Because all it is 2 protons and 2 neutrons, so there's no electrons to balance the charge. So being positively charged, they are deflected by magnetic fields. Okay. So symbolism. So let's talk about how we look at what we call nuclear equations. Okay, so we're going to start with a what is sometimes referred to as a parent element. So we're going to take a look at uranium-238. Okay, and what happens, uranium-238 undergoes alpha emission, and what you'll get is an atom of thorium-234. And an alpha particle. Okay, we will sometimes just use the symbol alpha to symbolize the alpha particle. Right? Things to pay attention to in this situation are the changes in the mass number. Right? So 238 becomes 234 with the loss of 4 mass number from the helium. And that should be not an H, but an HE, excuse me. Okay, and then the other thing to pay attention to is the atomic number. 92 becomes 90 plus 2. Okay, so with alpha emission, you will always have a change in the mass number of 4 and a change in the atomic number of 2. And that shows up over here with the helium nucleus. Okay, so the sum of your mass numbers on both sides should be even. So I have 238 on the left, and then on the right I have 234 and 4, which add up to 238. So everything should be balanced that way. My atomic number on the left, 92. On the right I have 90 and 2, which total to be 92. Okay, so this is an appropriate equation for alpha emission. Okay, so we refer to, I said that we refer to the uranium as the parent particle. The thorium is referred to as the, sorry, my handwriting is lovely, daughter particle, or the daughter element. Okay. Our next type of radioactivity is beta emission. Okay, and beta emission actually has two different types. The first one we'll talk about is the standard beta particle, and then the second type is actually referred to as a positron. Okay, so what happens with beta emission? That occurs with spontaneous conversion of a neutron into a proton. Okay, so when something that's neutrally charged spontaneously converts into something that's positively charged, you are ejecting a negative particle. So what we have is, because we are transforming a neutron into a proton, we see an increase in the atomic number. Remember that the atomic number is the number of protons in an element. And so with the increasing in atomic number, we have a loss of a negative particle. And we have the symbolism that looks like this. That is our negative charge. This is our mass number, and B for the symbol for beta. Okay, this is essentially an electron. Okay, has almost no mass, has a unit of negative charge. So a beta particle is essentially an electron. Okay, these are smaller, much smaller than alpha particles, but penetrating power is higher. Okay, smaller particle, but it can go through more matter. All right, so whereas we could stop a beam of alpha particles with a sheet of paper, a stream of beta particles, you would need something like a phone book. Okay, so in order to keep things safe, right? It's negatively charged, so it is also deflected by magnetic fields. Okay, but being negatively charged, it will be deflected in the opposite direction of an alpha particle, which is positively charged. Okay, so the sort of symbolism that we can put with this. So we could look at this in terms of a neutron all right, N for neutron, converts into a proton, P for proton, plus a beta particle. Okay. Okay. So we start out with a neutron that's has no charge, and we convert into a proton that is positively charged plus a beta particle which is negatively charged. Okay. So the other type of beta emission is what we call a positron. Okay? And a positron is essentially the same as a beta particle, just oppositely charged. So what happens with positron is when you get a proton converting into a neutron. Okay? Essentially the opposite process of beta emission, where beta goes from a neutron to a proton. Positron emission results from a positron becoming a neutron. So we would look at that and see a proton becoming a neutron, plus a positron. Okay? So what we see in these two processes, let's look at actual examples of the equations. So thorium-234 undergoing beta emission will become, I forget the name of this element, Pa plus a beta particle. Okay, so notice that the atomic number, or excuse me, the mass number, no change. Okay, the total number of protons and neutrons, the total, has not changed. All I've done is transformed a neutron into a proton. So with beta emission, we see an increase in the atomic number. We've converted a neutron into a proton, so we have one more proton. That means that we have a new element. Okay, so an increase by 1. Right. For our positron, let's take a look at how that works. So if I have phosphorus 30, can undergo positron emission and become silicon. Okay. Again, notice that the mass number didn't change because all I've done is converted a proton into a neutron, so my total number of nucleons is the same. But here with positron emission, we see a decrease by 1. Right? So our next type of radiation results in gamma radiation, but the cause of it is something called electron capture. Okay, so to clarify, beta emission, either beta emission or positron emission, beta radiation results from a spontaneous conversion of a neutron to a proton or a proton to a neutron. Electron capture, what happens there is when an inner shell electron is absorbed by a proton. When that happens, we take a positively charged thing, we add some negative charge to it, so what does it become? It makes a neutron. Okay, so beta emission is the spontaneous conversion. Electron capture is actually the absorption of an inner shell electron. Okay, and the result is gamma radiation. And we'll talk about that here in just a moment. And how that's different from other types of radiation. So the way this looks as far as an equation, example, we can have tantalum 202 plus an electron will become mercury 202. Okay, and then it's followed by gamma. Okay, so very similar to the change resulting from positron emission, but the cause is different. So we see the mass number stays the same because we're just converting a proton into a neutron, but because we're changing, we have one fewer proton, our atomic number goes down. So I promised we would talk about gamma rays. This is our last type of radiation. And it's the one that, probably most people through popular culture have heard of. So gamma rays, the thing that makes the Incredible Hulk so incredible. Okay? So gamma rays are a type of electromagnetic radiation. Okay? Similar to microwaves or UV radiation or infrared or visible light, it's all part of the electromagnetic spectrum. Gamma rays happen to be highly penetrating, high energy electromagnetic radiation. So what causes them is a nucleus losing energy. From an excited state. Okay, so gamma rays are undeflected by magnetic fields. Okay, and they are highly penetrating. Oops. Apparently I can't spell. Penetrating. Okay, so alpha particles, you can stop them with a sheet of paper. Beta particles, you can stop them with a phone book. With gamma rays, you need thick lead bricks. Okay, so highly penetrating alpha particles are. So let's take a look at the process of how we get gamma rays. So if we take a look at alpha emission from uranium, so uranium-234 undergoes alpha emission, becomes thorium-230, and we're going to show that it's an excited nuclear state by this thing called a double dagger. Okay, sort of looks like a cross with an extra bar. All right. So this is the excited state of thorium, of the thorium nucleus. And to finish our equation for the alpha emission, we'll also have our helium nucleus leaving. Okay? So the next step is for that excited thorium nucleus to lose that extra energy. Right? Just by losing energy, it doesn't change it from a thorium 230, but what we get and I'm not very good at drawing the gamma symbol, but this is our gamma emission. Okay, so gamma emission is common to accompany other types of radiation. So you don't always just have alpha emission all by itself, or beta emission all by itself, or electron capture all by itself. Usually those changes result in an excited state of the nucleus and then followed by an emission of the gamma ray as that excited state relaxes back down. Right. So that pretty much does it for our nuclear equations. So let's just do a quick little recap of some of this stuff. Excuse me. So with alpha emission, we see a change in the mass number. Okay, that mass number will go down by 4, and our atomic number will go down by 2 as a result of that alpha particle. Okay. With beta, depends on whether you're dealing with beta or positron. Okay. With beta emission, with either type of beta emission, you'll have the mass number showing no change. But if you have beta emission, your atomic number will increase by 1. And if you have positron emission, your atomic number will decrease by 1. But in both cases, your mass number stays the same. With electron capture, again, your mass number will stay the same, and this time your atomic number will decrease by 1. Very similar to positron emission, but for a different reason. And then gamma rays, we actually don't see, specifically from the gamma emission, we don't see any change in mass number or atomic number, but it's the result of an excited state that usually comes along with other types of radiation. Okay. So our next topic is radioactive decay. Okay. And much of what we know about radioactive decay comes to us from Marie Curie, who was a pioneer in the field of radioactivity. She essentially discovered it. And unfortunately for her, that resulted in severe radiation poisoning, which eventually killed her. To this day, her laboratory notebooks and things are too radioactive to handle. You actually have to wear a suit in order to even manipulate those lab notebooks. And she died over 100 years ago. But she is one of the few scientists in all of history to have 2 Nobel Prizes. So, good for her. So radioactive decay is proportional to the amount of material you have. Okay, and we have an equation for that. So the rate of decay is related to the activity, A, which is related to a constant, the decay constant, and the amount of material present. This is our decay constant. Okay, and it'll be in units of time, so it'll be time to the -1. So, and that could be seconds, minutes, days, years, just depends on the scenario. And N is the amount of material. Okay, so we're going to revisit an old friend from a previous chapter, and that is half-life. Okay, so remembering that half-life is the time it takes for 50% of the material to disintegrate. right? And lucky for us, half-life for radioactivity follows first order. So if you remember, T1/2 equals 0.693 over K. Okay, so pretty simple. It's not one of the horrible like second order half-lives where you have to do extra things. It's a pretty straightforward equation. So at any given time, okay, we can tell either how much material is left, how much, depending on how much we started with, or vice versa, by the following equation. We have natural log of n at time t over n at time 0 equals negative kt. Okay, remember n is the amount of material. So n at time t is the amount at time t, and n0 is the initial amount of material. Right? K is still our decay constant. Okay? So one thing that's going to be useful to you in doing these problems is just a quick little review on how logarithms work. Okay, how to manipulate logs. Okay, so if we have K equals the natural log of C, then e to the k equals c. Okay, so if I have a natural log and I take e to both sides, then this is the result. So if I need to know what c is, then take e to the k power. Okay, so if I have natural log of x times y, that equals the same thing as natural log of x plus the natural log of y. Okay. If I have the natural log of x over y, that equals natural log of x minus the natural log of y. Okay. And another useful one here, natural log of x to the y power is the same thing as y times the natural log of x. Okay, so these manipulations of logarithmic equations will come in very handy when trying to figure out how much material is there, how much was originally there, and things of that nature. Okay, so let's take a look at some applications of this. One of those is carbon-14 dating. And no, that's not a bunch of carbon atoms going on dates. Sorry, I had to say it. So carbon-14 dating is based on the half-life of carbon-14 in living things. All living things contain a replenished amount of carbon-14. So while things are alive, they have a standard amount of carbon-14 because we get it from our environment all the time that we are alive. Okay? But when something dies, the rate of disintegration changes. Okay? In living things. I forgot to finish that sentence. Okay? So let's do a little practice. All right? So using half-lives and figuring out how much material should be there after a given amount of time. So here's our practice. So for example, you have 22.5 grams of iodine 131. 53. which has a half-life of 8.04 days. Okay. So the question is, how much material will you have left over at, let's say, 3.4 days from now? Okay. So first thing, step one is we need a decay constant. Okay. So let's take a look at our half-life equation. So T1 half 0.693 over K, right? So we need that K value. This is what we're after. Okay? And this problem is very, very much like the type of half-life problems that we did previously when we were doing kinetics. Okay? So since I know what the half-life is, I can rearrange my equation and say K is 0.693 over T1 half. Okay, in this case, 0.693 over 8.040 days. All right, so my decay constant will equal 0.08619 days to the minus 1, so inverse time. Okay, remember that our decay constant should be in some time to the minus 1. So, and like I said, it can take different forms. It can be seconds, it can be years. In this case, it's days. Okay. So now that I know my decay constant, step 2 is to find n at time t. So how much material is left at a given time? In this case, 3.4 days. So we have our equation, ln of nt over n initial equals negative kt. Right, so if I rearrange this equation using my tricks with logs, I can say n at time t over n0 equals e to the negative kt. And so if I do a little further rearrangement, I get n at time t equals e to the negative kt times n initial. Okay. So n at time t equals e to the negative 0.08619 inverse days times 3.4 days times 22.5 grams, which is our initial amount of material. Okay? Plug through that little bit of calculation and we'll find that the amount of material left after 3.4 days is 16.8 grams. Okay, so manipulation of the log equation was certainly did come in handy for us. Right, so let's apply this to a slightly more practical example. So carbon-14 dating. How old is a fossil if it has, if it has 36.2% carbon-14 left? Okay, so T1 half for carbon-14 is well known 5,730 years. Okay, that's a well-established value. Okay, so our fraction remaining, so if I have 36.2% left, 36.2 over 100%, 0.362. And so my fraction remaining, I have a handy relationship there that looks like 0.5 to the t over t1/2 power. Okay, so since I know the fraction remaining and I know the t1/2, I can solve for t. Okay, so let's plug in some values here. So our fraction remaining is 0.362. We plug into our fraction remaining equation, so it's t over 5,730 years. Okay, so how are we going to solve for t? We're going to use logs. All right, so we do a little manipulation. We take the log of both sides. So we say the log of 0.362 equals t over 5,730 years times the log of 0.5. Okay, so I'm going to scroll back up to our logs and just show you which one we just used. Right, so we just used this one. Okay, so if I take the log of both sides, it doesn't have to be natural log. Log base 10, the rules are the same. Okay, so let's come back down. Right, so now that I've got this set up this way, log of 0.362 divided by the log of 0.5. Okay, now this is different than saying the log of 362 over 0.5. Okay, you need to take the log of each of those values and then divide them times 5,730 years. So we find out that the fossil is 8399.8 years old, or about 8,400 years. Okay, so if you're ever wondering how they have gone about, how archaeologists and such have gone about figuring out these ages of things, this is how they do it. They are able to measure the amount of carbon-14 left in an object, and then they use these calculations to arrive at an age for some sort of thing that used to be living. Carbon-14 dating doesn't work for things like rock or, things that were never alive. They have to use different aging methods for those. But anything that used to be living has some amount of carbon-14 left in it that has decayed at a predictable rate. So our next topic here is called transmutation. Which to me always sounds like something that an alchemist would do, is transmuting lead into gold. But in our case, in modern science, essentially what we're doing is we're smashing things together. Smashing elements together in particle accelerators to make new elements. Okay, so all of the elements past about 92, we have been able to make in the laboratory by way of transmutation. And in fact, elements like 114 to 118, the only way you can make them is by this method. Okay, so important things looking at problems with transmutation in your homework and such is that the atomic numbers in the equation of the reactants add up to the atomic numbers of the products. atomic numbers of reactants add up to the atomic numbers of the products. Okay, and same goes for the mass numbers. Okay, so let's look at an example. It's probably the easiest way to think about things. So let's say I have some iron 58. I'm going to bombarded with a stream of neutrons. Okay, so I'll start out with, still never figure out how I start writing a 5 and it ends up as an oval. 58, 26. Start out with some iron, and I'm going to smash into it with some neutrons. My result will be a new isotope of iron. Okay, so notice that the mass numbers, 58 plus 1 equals 59. My atomic numbers, 26 and 0 equals 26. Okay, so everything still needs to be balanced. Okay, so look at another example. So if we have, for example, some plutonium-239, bombarded with alpha particles. Okay. Let's take a look at what that shapes up like. So I'll have 239, 94 plutonium. And I'm going to hit it with a helium nucleus, an alpha particle. Okay. What I get is an element that I can't recall the name for, Cm, curium perhaps. Suppose before doing this video I should have looked these things up, but the names of the elements are not what I want you to focus on. Okay, so let's see. So 239 plus 4 should equal 243. 94 plus 2 should equal 96. So look on the right side of my equation. 242 plus 1 equals 243. So my mass numbers match on right and left. And 96 plus 0, my atomic numbers match right and left. Okay, so all these things have to be balanced. Okay, so our last topic for the chapter is a thing called mass defect. And along with mass defect, we're also going to talk about binding energy. But mass defect, what it is the difference between an atom's actual mass and the calculated mass of the sum of its nucleons. Okay, its nucleons being the protons and neutrons. Actual mass and the calculated mass of its neutrons. I said neutrons, I meant nucleons. And just to clarify, when we say nucleons, we're talking about the protons and the neutrons. Okay? So what they found was, once they determined what the mass of a proton was and the mass of a neutron, and so they said, okay, a helium nucleus should have, a calculated mass of somewhere around 4 AMU. And what they found experimentally was that the mass of the helium nucleus was close, but not quite. Not quite what they calculated it should be. So that's what we refer to as the mass defect. And all that is taking the atomic mass, subtracting it from the calculated mass of the total of the nucleons. It's a very simple process. I actually think that you can probably handle it without an example. But the part that I do want to go over is how it's related to nuclear binding energy. Okay? And nuclear binding energy is the energy needed to break apart a nucleus. Right? And this leads right into topics of like fission and fusion and nuclear weapons, and all that sort of stuff comes from these concepts of nuclear binding energy. It's the energy it takes to break apart a nucleus and start a nuclear reaction. Right? And lucky us, we get a very famous equation to play with. E equals mc squared. So any change in energy is proportional to a change in mass. Okay? So let me just write that down before I go away. Proportional to change in mass. Okay? And that change in mass is our mass defect. Okay? So let's do a little example on how to calculate binding energy. Calculating binding energy. There are a couple of things that will be useful to you in doing these problems. So useful is, one is the knowledge that 1 gram is equal to Avogadro's number worth of AMU. Okay? Because we need mass, not atomic mass units. Okay? And our mass defects are always going to be calculated in atomic mass units. The other one that is useful is, because we're talking about energy, is that 1 joule is 1 kilogram meters squared over seconds squared. Okay? So remembering that c is the speed of light, and that's in meters per second. And we're going to square that. Okay? So that gives us our meters squared over seconds squared. So our mass needs to be in kilograms. Okay? So that's why we want the conversion of AMU to grams, which we can then convert to kilograms. Okay? So let's do a little example problem. Example. Let's calculate the binding energy if we are given a mass defect of 0.03038 AMU. Okay, so in our E equals mc squared, I'm going to plug that mass defect in right there. Okay, essentially what it does is it turns this equation into delta E equals delta M times c squared. Okay, so I'm going to plug my mass defect, which is the change in mass, into E equals mc squared. Okay, so let's convert our AMU to kilograms, and that will make our lives a little bit easier to get into the equation. 0.03038 AMU, Avogadro's number, worth of AMU per gram converted to kilograms. Okay, so we'll find that our mass defect in kilograms is a rather preposterous times 10 to the minus 29 kilograms. Okay, still more massive defect than the mass of an electron. Mass of an electron is to the power 31, minus 31 kilograms. Okay, so now that I know what the mass defect is in kilograms, I can plug it into E equals mc squared. So delta E equals our mass defect in kilograms times the square of the speed of light. Okay. So we'll find that the binding energy is 4.534 times 10 to the minus 12 kilograms meters squared over seconds squared, or joules. Okay, so binding energy is super cool. Understanding how to calculate the energy that holds a nucleus together and the energy that required to break it apart and creates nuclear fusion.